By making small changes in the model we are analyzing, sometimes we can make the problem easy to analyze, and we can use those results to bound the solution we expect from detailed analysis. Our goal is to change the situation in some way to make it easy to analyze so we are less likely to make a mistake. There's a wide range of quantities that we might be interested in. A reaction value, internal shear or moment at a critical location, displacement at a certain point. Choose one or two quantities to focus on. To find those one or two quantities more easily, we might change the loading. For example, calculating the peak displacement for a beam with trapezoidal loading requires methods we cover in later chapters. But if we convert that loading to a uniform distributed load, there is a formula for peak displacement already derived. We might change the boundary conditions, the supports or connection type. For example, this beam is indeterminate, but if we change the fixed support to a pin support, this beam is determinate. We can find the peak shear and moment in this beam quickly. The third type of change we make is to the geometry. Finding the peak moment between the supports in this beam takes several minutes. But if we ignore the cantilever that overhangs the right side, we can find the peak moment easily. We make a change in order to simplify the calculation, but that means we are getting an approximate result for the quantity we are focused on. By thinking through the impact of our change, we can deduce whether the quantity we are focused on will increase or decrease compared with the detailed analysis of the original structure. If the quantity will increase because of our change, that result is an upper bound for the quantity for the original structure. For example, consider this loading. This is what dead load would look like on a beam supporting a two-way floor. If we increase the distributed load all along the beam to be equal to the magnitude in the middle, then we have increased the total applied load. If the quantity we are focused on is the peak moment, increasing the total load on this simply supported beam will increase the internal moment. Therefore, the peak moment we calculate from this approximate loading will be an upper bound on the peak moment for the original loading. Similarly, if the quantity will decrease because of our change, the result is a lower bound for the quantity for the original situation. Let's consider this same example. If our simplification is to reduce the distributed load to be uniform at the magnitude at the ends, we are decreasing the load everywhere except the ends. So the peak moment will decrease. That means we have determined a lower bound on the peak moment for the original loading. How is this helpful? After we perform detailed analysis, we take a look at the quantity we chose to focus on. If the magnitude of that quantity, that moment or displacement or reaction, is bigger than the upper bound we obtained in the simplified prediction, we know that there is a mistake somewhere, and the mistake is probably in our detailed calculation. We can usually determine the effect of one change. The challenge is when we make more than one change in order to get the structure simple enough to analyze quickly and with confidence. To figure it out, we need to use superposition. Consider the effect of each change separately on the quantity we are focused on. If each change causes the quantity to increase, we still know that the approximate result will be an upper bound for the detailed result. For example, consider this trapezoidal loading on a beam with a cantilevered end. If we are focused on peak downward displacement between the supports, we might choose to move the roller out to the end and change the loading to uniform distributed load at the peak magnitude from the original structure. The loading on the cantilevered end helps draw the beam up between the supports. By moving the roller out to the end, we have more load between the supports, which causes more downward displacement, and we no longer have the cantilever lifting the middle up at all. Therefore, this change increases the predicted peak displacement. Adding load to make it uniform distributed load also increases the predicted peak displacement. So both changes result in increased displacement. That means we still get an upper bound on the displacement we will calculate with detailed analysis of the original structure with the original loading. Sometimes we make changes that have competing effects. One change causes an increase in the target quantity, and one change causes a decrease in the target quantity. For example, what if we want to predict the peak moment in the beam of this portal frame with a triangular distributed load? The rigid connections between the beam and the columns result in negative moments at the ends of the beam. If we simplify the beam as being simply supported, those moment restraints go away and we get an increase in the peak moment at midspan. But we still have the loading to deal with. If we replace the triangular distributed load with an equivalent uniform distributed load, we've taken some of the load from the middle and moved it out to the ends of the beam. Moving some load toward the supports results in a decreased peak moment. In order to get an easy-to-obtain approximate peak moment in the beam, we needed to make two changes. One change caused an increase in the peak moment, and the other caused a decrease in peak moment. We can't tell which effect caused the bigger change, so we don't know if the net effect is an upper or lower bound. However, we do know that we have an approximation that can be useful for comparing with our detailed result.